In this video series, we're going to talk about the basics of electrical measurements. And we're going to start with motivation and central ideas that we're going to use to understand electrical measurements. You might be asking, why study electrical measurements at all? Circuits aren't perfect, they require some expertise to use, and they can go comically wrong when they're misused, like this circuit on the left. But they can enable us to take really remarkable measurements, like the figure on the right. This is data from the Laser Interferometric Gravitational Observatory, or LIGO, which has measured distortions in space-time from black holes. This data shows that the proof masses in LIGO have a noise of 10 to the negative 22nd per root hertz, which is remarkable, but the electrical measurements they took of those proof masses have to be even better than 10 to the negative 22nd. So electrical measurements can be extremely sensitive. And it's worth noting that even when we're looking at something non-electrical like a proof mass, we take an electrical measurement of it. So reason one to study electrical measurements is they can be very sensitive. But part of that sensitivity also comes from the rich mathematical treatment we can give them with computers. And it's worth noting that electrical measurements are particularly easy to interface with computers. So to summarize, we need to learn how to take electrical measurements because they're matter for any kind of experiment, they're extremely sensitive, and they're very convenient. One way we're going to try to generalize the idea of an electrical measurement so that we can make broad statements about electrical measurements as a whole is to reflect that every electrical measurement has three parts. Some kind of stimulus, some kind of circuit under test, which can be as simple as a wire for some examples, and some kind of measurement. There are lots of examples of each of these types of things. Stimuli can be signal generators or power supplies. Measurements can be multimeters or oscilloscopes. And we're going to have specific videos that talk about the details of each of those devices and how they fit into our electrical measurement framework. But first, we need to define our framework, which consists of three big ideas in this video. And these ideas are so pervasive through this video set that they're absolutely worth understanding. We're going to use them as a shorthand in all of the videos to follow, so make sure you dig into them carefully. The first big idea we're going to talk about is equivalent circuit representations. And our central goal with these is to take complicated experimental setups, like the one on the left, and turn them into simple circuit representations, like the one on the right. Both of the parts of this left circuit setup are tricky. Oscilloscopes are complicated digital systems, piezo tubes have fancy materials in them, and it would be hard to model them. But we can still make educated statements about how they behave together if we can reduce them down to an equivalent circuit. So our goal is to take complicated things in the real world and make simple models for them. And over the next several videos, I'm going to give you simple models for tools that you use in the lab, multimeters, oscilloscopes, etc. So to be super explicit, in this equivalent circuit model, the oscilloscope has been replaced by a resistor and an ideal voltage measurement. The ideal voltage measurement is denoted by the plus and minus V scope. And because we're representing the scope as a resistor, we'd often call this resistance, the R scope in this picture, the input resistance of the oscilloscope, or the load resistance of the oscilloscope. Similarly, we've replaced our piezoelectric element with this voltage source V piezo and this series resistor R piezo. This series resistance would be called the source resistance or the output resistance of the piezo tube. This model is super common, where we represent some sort of voltage generating thing as a small voltage source in series with a large series resistance. And in fact, for the piezo tube, V piezo would also often be a few millivolts, and R piezo could go up to gigaohms. And that model is so common that we give it a special name. This is a model for a transducer. And transducers are devices that turn non-electrical signals into electrical ones. The second big idea that we need to focus on is loading, which is a code word for saying that when you hook electrical things together, they can affect each other's inputs and outputs. So for example, if we look at the same experimental setup that we had on the last slide, we can try to use our equivalent circuit model to analyze the behavior of the circuit. The equivalent circuit model is over here. So even though this equivalent circuit model contains kind of a scary dashed line, we can treat it just like a normal circuit. The scary dashed line is just there to remind us that we're dealing with models of things and not with actual resistors and voltage sources. So ignoring the line, we see this is a simple voltage divider. And that tells us that V scope, the voltage we measure, is equal to R scope divided by the sum of R piezo and R scope. That means the voltage that appears on the oscilloscope isn't the same as the voltage that's generated by the piezo. So the voltage we're trying to measure isn't the voltage we actually measure because the oscilloscope itself influences our measurement. This change in sort of measured voltage is called a loading effect. We could also say that in this case, the oscilloscope is loading the piezoelectric tube. In this specific case, by the way, I'd call this instrument loading because it's our measurement instrument that's causing the loading. Now, in the oscilloscope video, you're going to learn that R scope, the load resistance here, is about 10 megaohms. But on the last page, we learned that our piezo could be as big as a gigaohm. So that means that our oscilloscope won't measure any signal at all from this transducer. Now, we can play special tricks to get around that, and much of E80 is learning what those tricks are and when to deploy them so that you can take good experimental measurements out in the wild. But one of the big ideas that you need to keep in your head whenever you're dealing with an electrical measurement is that your instrument or your circuit could be loading your measurement or your stimulus. The last big idea that we're going to come back to over and over again as I describe different instruments is the idea of referencing. Most instruments measure or produce voltages, and voltages are always defined between 2 points. Similarly, when I talk about measuring a voltage, I talk about measuring it relative to some reference. But one of the tricks in electrical measurements is that different instruments don't always agree what the reference should be. So when you hook instruments together, you can cause surprising behavior when their references get in fights with each other. So in the next several videos, as we describe these new instruments, I'll tell you what they're referenced against, but you always need to keep a picture in your head of what references need to be hooked together and what references don't. Now, to try to get you an idea of what's going on with a reference, I've drawn this circuit up here that has an oscilloscope sketched attaching to it. The oscilloscope is always referenced against a special kind of ground called an earth ground, while this circuit depicts a different kind of ground down at the bottom. That means that these two grounds could be at very different voltages. The earth ground is whatever's coming from the wall. This other ground usually implies that it's some kind of isolated ground that doesn't care about wall voltage at all. But both of them might be asserting themselves as ground very forcefully, and that means you could get a short circuit where the two grounds try to drive current into each other. That's referred to as a ground fault, and it's really surprising and results in lots of kind of alarming short circuit warnings on your power supply. So we need to pay attention to what our instruments are referenced against, and what grounds we can hook together, and what grounds we can't. And the two main types of grounds that we'll run into are things called isolated grounds, which can be connected anywhere without too much trouble, and earth grounds, which all have to be connected together, because if there's ever a disagreement between earth ground, you get a short. So in conclusion, we're going to study electrical measurements because they're really sensitive and they're easy to digitize, and we're going to analyze those measurements by thinking about a couple of big ideas. One is the idea of equivalent circuit models, so we're going to represent tricky real-life things by simple circuits. One is the idea of loading, which is to say when we stick those simple circuits together, often they will affect the voltages that appear at our measurement devices. Or put another way, our instruments can influence the voltages that they're trying to measure. And finally, we're going to think about measurements by paying attention to where the measurement is referenced, because different grounds can interact in really nasty ways. So upcoming lab videos are going to describe lab equipment using those three big ideas.